In this section, we're going to look at an informal introduction to limits using graphs and numerical tables.
Now, as a disclaimer, in this section we are going to look at a concept called a limit. We are not going to look at it formally, however. We're going to take a look at an informal concept, an informal view of the concept of a limit. There is a formal way of expressing that, and it is a bit more involved, but for now we're looking at the informal method largely to gain some intuition, to gain some idea as to what this all means. Right? So consider a function. Let's say I have f of x is equal to x squared minus 9 over x minus 3. Okay, and now I could plug in numbers into this function. I could say, all right, I'm going to find f. I can find f of let's say 5, and that would simply be 5 squared minus 9 over 5 minus 3. Okay, well, 25 minus 9, that's 16, and 5 minus 3 is 2, and that would give us 8. And I could do that with just about any number. I can plug in most numbers and evaluate. And of course I might get some nice whole number, I might get a fraction or a decimal, but I'll usually get some answer. Now when I say usually, that's because, well, there is one particular case where I don't get anything. If I try to plug in number 3, I get 3 squared minus 9 over 3 minus 3, which is 9 minus 9 over 3 minus 3, or in other words 0 over 0. Which is undefined. I don't get anything because this is not a number. Okay? So here I can't find the function evaluated at 3. Okay? But now I'm going to ask a strange question, one which seemingly is nonsensical, which doesn't seem to have an answer, and then we'll investigate how we might formulate an answer. Okay, so what do I get when I plug in 3? Well, I can't. All right. I try it, it doesn't work. It gives me some nonsense. Okay, fine. But what if I could? What if I could plug in 3 and get something? Well, that would be nice, but I can't. So I can't, and that's it, I'm done. Well, okay, sure, it's true, I can't. But what if I could? This seems like a strange question. You know I can't, so what do you mean, what if I could? Well, that's what we're going to investigate here in an informal fashion. Here, what I'm trying to do is I'm trying to get an x value of 3. Okay? So whenever I plug in an x value to a function, then I get a y value, or an f of x value. Okay? So right now what I wish to do is I wish to plug in the number 3. But again, we know we can't do that. Okay, but well, there are other numbers I can plug in, right? Sure, I can plug in number 2. And you say, well, okay, fine, but that doesn't do you any good because you're trying to plug in number 3. So right now I'm going to say something else that sounds a little strange. Well, maybe that's close enough. Right? Maybe if I can't plug in 3, maybe plugging in 2 is the next best thing. So let's see what happens there. If I plug in number 2, 2 squared is 4. 4 minus 9 is negative 5. 2 minus 3 is negative 1. Negative 5 over negative 1, that's a positive 5. Okay, so that's kind of a strange statement. I want to plug in 3, and I know I can't, so let me plug in 2 and see what happens. Okay, well, I got f of 2 is 5. It still doesn't tell me what f of 3 is. In fact, f of 3 can't be anything. So what good did that do? I say, well, you know what? Maybe I said plugging in the number 2 is close enough. But maybe it's not close enough. Maybe I can do better. Maybe I can plug in a number that's closer to the number 3. For example, I could plug in 2.5. And let's see what happens if I plug in 2.5 here. All right, well, let's see. 2.5, if I square that and subtract 9, that gives me a numerator of negative 2.75. And now I'm going to divide that by 2.5 minus 3, which is negative 0.5. And if I do that, I get 5.5. And I mean, I guess technically what I've done is closer to plugging in the number 3 than I did before, but that's still not really an answer to what I want. I want to know what happens when I plug in 3, and I know I can't. Well, I plugged in 2 and 2.5, and I got answers, but what do those have to do with this? Well, then I say, well, you know what? Maybe I can do better, because I'm trying to plug in a number close to 3, and these aren't really that close. Maybe if I get really close, I'll get some intuition. I'll get some knowledge of what should happen. Let's see what happens if I plug in 2.9. Okay, well, let's see. 2.9 squared minus 9. That gives me that as my numerator. Divided by 2.9 minus 3. That gives me negative 0.01 as my denominator. And when I divide, I get 4.9. Oh, sorry, 5.9. Okay, well, I'm plugging in numbers that are getting closer to the number 3, but I still haven't plugged in the number 3. In fact, I know I can't. Now, you might ask, well, why are you plugging in numbers that are less than 3? Couldn't you plug in numbers greater than 3? Well, yeah, I could, but I mean, it would suffer the same problem. It would be close to 3, but it wouldn't be the number 3. All right, well, let's see what happens if I do that, though. Maybe I'll gain some kind of information that I didn't already know. If I plug in the number 4, 4 squared is 16, minus 9. All right, 16 minus 9 will give us 7. 4 minus 3 is 1, so 7 over 1, which is just the number 7. All right, well, just like before, I said, hey, I'm trying to plug in a number I'm trying to plug in 3, and 4 is kind of close to 3, but you know what, I can do better. Maybe plug in a number that's closer to the number 3 than the number 4 was, maybe 3.5. Okay, so let's see what happens. 3.5, if I square that, minus 9, that's a numerator of 3.25. Divided by, if I plug in 3.5 and I subtract 3, that'll give me 0.5. And if I finish that division, that gives me 6.5, 6.5. But just like before, I can say, well, you know what, maybe that wasn't close enough. Maybe I can do better. Let me get closer to the number 3. For example, I can use 3.1. All right, well, what happens if I plug in 3.1? Now, let's see. 3.1 squared minus 9. That's 0.61 as my numerator. Divided by, and now that's going to be 3.1 minus 3. That's just going to be 0.1. And if I divide those, I get 6.1. Okay. And in both cases, here, whether I started with the number 2 or I started with the number 4, what I'm doing is I'm trying to plug in numbers that are closer to what I actually want. Okay, but, well, now you might say, well, so what? It doesn't matter what numbers you plug in. Even if they're close to 3, you're still not plugging in the number 3. And I say, well, you know what? Let me go for broke. Let me plug in a number super close to the number 3. Now, I can do it from either side. Here, a number that's bigger than 3, that's super close, would be something like 3.0001. Or over here, something that's super close but slightly less would be something like 2.9999. And in both of those cases, I'm not plugging in the number 3, but I'm very, very close. Let's see what happens if I plug in those numbers. Let me start with 3.0001. All right, 3.0001. If I square that and subtract 9, I get 0.00060001. And I'm going to divide that by 3.0001 minus 3. Well, that'll give me just 0.0001. And when I finish that division, I get 6.0001. 6.0001. All right, I tried to plug in 3.0001. Let's try 2.9999. Let's see what happens there. 2.9999. If I square that and subtract 9, I get a numerator of negative 0.00059999. Now let me divide that by 2.9999 minus 3. That'll give me negative 0.0001. And when I divide those, I get 5.9999. Okay. Notice that I never actually plugged in the number 3 because, as I've established and stated multiple times, I can't. But look what happens as I plug numbers in that are close to 3. Notice what happens to these y values as my x value goes from 2 and gets closer and closer to 3. Well, 5, 5.5, 5.9, 5.99999. Look what happens when I start with 4 and get closer and closer to 3. 7, 6.5, 6.1, 6.0001. What pattern do both of these have? they're both getting closer to the number 6. Here, 7, 6.5, 6.1, 6.001, that's getting smaller and smaller and closer to the number 6. Here, this is getting bigger and bigger and closer to the number 6. So here, it looks like if I plugged in the number 3, I should get the number 6. Oh, but I know that's not true. I can't do that. Okay, so f of 3 is not 6. It's undefined. And that is a matter of fact. It is undefined. However, if I could plug in the number 3, it seems like I should be able to get the number 6. LIM. This is read as the limit of something. The limit as x approaches 3 of x squared minus 9 over x minus 3 is equal to 6. This is how we summarize the results of this table here. Notice you're not saying x is 3. You're saying x is approaching 3. That's what this little arrow says. It says you're getting closer and closer to the number 3. As you get closer and closer to the number 3, your answers get closer and closer to the number 6. You're not saying you actually plugged in 3, because that's impossible. Instead, you got closer and closer to the number 3. This right here is, in words, would be read as the limit as x, and you can either say approaches 3 or goes to 3. Both of those are fine. I'll write approaches, but you can say goes to, and that's fine. Approaches 3 of my x squared minus 9 over x minus 3 is 6. That's how you would read this. The limit as x approaches 3 of this expression is 6. Right now, we're not formally defining what we found. All we're saying is, from this table, we have a pattern that we've established. Okay? Once we start being able to see this pattern more and more reliably, then we will formally define what it is that we're finding. But for now, we're doing it informally by looking at this pattern. So let's see another example of this. All right, so for the next example, we're going to say, all right, let's find, and now let's actually go ahead and start with this notation. I want to find the limit as x approaches 0 of the sine of x over x. Right here, what I'm saying is I wish I could plug in the number 0, but you know what? I can't, because the sine of 0 is 0, and 0 over 0 is undefined, so I cannot. Okay, so I cannot. But up here I couldn't plug in the number 3. What I did was I plugged in numbers close to 3 and looked for a pattern as I got closer and closer to the number 3. Over here, I'm going to do the same thing. I'm going to look for a pattern as I approach not the number 3, but the number 0. So I'm going to plug in values of x and find what that will provide as an f of x. All right, so let's take a look. All right, in the middle, I'm going to put 0 because I want to be able to find what happens as I approach 0. And what I'm going to do is I'm going to pick a number on either side of 0 and start to close in on 0. Now you might say, well, why do I need numbers on both sides? Couldn't I start from over here and just say what happens as I go up to 0? Or couldn't I just do this side and see what happens what goes down to 0? We'll see this in the next example, but sometimes what happens from one side will be different from what happens to the other side. Here, on both sides, your numbers were getting closer to 6. In this example, you will also have your numbers will get closer to some number. However, as we'll see in the third example, you don't always have that. In that case, that means something else that will be meaningful to our result. Okay, but for now, you will have the same thing happening on both sides. But we do have to confirm what happens on both sides because they won't always be the same. If they're different, well, we'll talk about what to do with that in the next example. So here I'm going to pick a number greater than 0. I usually just pick the next number up, 1, and the next number down is -1. Okay, so I'm going to go ahead and plug in those numbers into sine of x over x. Here, since that's not 1 degree, it's just the number 1. Right here, that's not 0 degrees, it's just the number 0. That means we're dealing with radians. So let me put my calculator in radians. All right, so here we go. I'm going to take the sine of 1 and divide by 1. And that's 0.8415. I'm going to round off to 4 decimal places. All right, what about negative 1? Well, if I take the sine of negative 1 and divide by negative 1, well, I still get 0.8415. Okay, 0.8415. All right, let's go ahead and move in closer. What's a number that's closer to 0 than 1? Well, maybe a half. Say 0.5. You could have said 0.2 or 0.3. Any number's fine, as long as you're getting actively closer to 0. And then from this side, I'm going to keep everything symmetric. I'll say negative 0.5. You don't have to. You could have said negative 0.3 and positive 0.5. But again, these are my choices to make, so I'm going to choose those. So if I plug in 0.5, all right, sine of 0.5 divided by 0.5, that's 0.9589. And if I plug in negative 0.5, take the sine of that, and divide by negative 0.5, I still get the same number, 0.9589. Okay. Let's try a number that's even closer. Let's say 0.1. And over here, let me use negative 0.1. Okay. All right, 0.1. If I take the sine of 0.1 and I divide by 0.1, I get 0.9983. 0.9983. If I use negative 0.1, take the sine of that and divide by negative 0.1, I still get 0.9983. So it looks like it's doing the same thing on both sides. Sometimes you'll have some symmetry, other times you won't, like in the previous one, these weren't the same numbers. Each example will be different. Okay. All right, so now I've started with 1 and negative 1, and I moved in significantly closer to 0. Now, let me go and pick a number that's really close to 0. Let's say 0.001, and let's say negative 0.001. And let's see what happens with those. All right, 0.001, if I take the sine of that and divide by 0.001, I get 0.999999 on like that. And if I plug in a negative, 0.001, I'm going to get the same thing, 0.9999. All right, so what's happening? 0.84, 0.8, 0.95, 0.99, 0.9999. What are these getting closer to? They're getting closer to the number 1. So does that mean that the sine of x, does that mean that the sine of 0 over 0 is equal to 1? No. The sine of 0 over 0 is undefined. That is a very important distinction to make. That doesn't mean you can plug in 0. Sine of 0 over 0 is undefined. We didn't suddenly learn how to divide by 0. What we have said is that the limit as x approaches 0. When you say this, that means you didn't plug in 0. You plugged in numbers that are extremely close to 0. The limit as x goes to 0 of sine of x over x. That's going to equal to 1. Right? You did not plug in 0. Because 0 over 0 is undefined, and we didn't suddenly make it defined. We didn't suddenly learn how to divide by 0. But the limit is equal to 1. All right, now, when we talk about limits, here we're approaching from one side and from the other. Now, what if you wanted to just talk about one side? What if I wanted to see what happens as I come closer to 0 just from the right? Or, conversely, just from the left? Well, then we can ask for that one. And there's a notation for this. If you ask for the limit as x approaches a number, so here I'm going to say c for constant, just some number, of a function, this is read as the limit as you approach c. Right? Your x value is getting closer to c. Now, what if you want just one side or the other? Well, then you make a slight modification to your notation. If you want to come in from the right, you're going to put a little plus sign right here. That means you're coming in from the right. If you think of a number line, positives are to the right, negatives are to the left. Here, the little plus sign means you're coming in from the right. This is read as the right-sided limit, meaning the limit from the right. Right-sided limit. As you approach C from the right. So that would be this side over here. When you're coming in from numbers that are bigger. If you want to come in from the other side, from where the numbers are smaller, from the left, well, that doesn't take a lot of imagination. If from the right you put a plus here, from the left you're going to put a minus. Note, these plus or minuses do not change this number. They're simply telling you what direction you're coming from. So here, if I want the limit as I approach 3 from the left, I would write this as limit as x approaches 3 with a little minus sign here. And that would not suddenly mean I'm trying to approach the number -3. I'm still trying to get to 3. I'm just trying to do it only from the left side. All right? So the plus and the minus do not affect the number itself. They only affect what side you're looking at. So this is the limit as x approaches c from the left of f of x. So this is called the left-sided limit. And it's what happens as you approach c from the left. Okay. All right, now in both of the examples we've seen so far, both of those sided limits are equal to each other. If you come in from the left, it looks like your number is getting close to 6. And if you come in from the right, you're also getting close to 6. So the two sides are the same. Same over here. If you come in from the left, you're getting closer to 1. And if you're coming in from the right, you're also getting closer to 1. So it seems that our limits agree on both sides. However, that's not necessarily the case. Okay, so what happens when they're not equal? Well, then you don't have a limit. Here, if the limit as x approaches c from the right of f of x is equal to L, some L for limit, some number, and that's equal to the limit as x approaches c from the left of f of x, then the limit as x approaches c, not from the left to right, but just the limit of f of x is equal to L. In other words, if both of them equal to the same, if they're both equal to each other, the way we say this is that the two sides agree. Here we read this as if the sided limits agree. If the sided limits agree, meaning they're equal to each other, then overall your limit is equal to that. However, if they are not equal, if the limit as x approaches c from the left of f of x equals to, say, L, and the limit as x approaches c from the right of f of x is equal to some other number, like let's say k, such that L and k are different. So in other words, the two limits are different from each other, they do not agree, then the limit does not exist. The limit as x approaches c of f of x does not exist. Okay? So if the two limits are the same, then that's your limit overall. But if the two-sided limits are not the same, then you don't have a limit overall. It does not exist. That doesn't mean we need to fix it. It just means it just didn't exist. We didn't have one. So let's take a look at some examples of sided limits where they might or might not be the same. All right, let's consider this. Example. Let's go ahead and try to find the limit as x approaches 0 of f of x. And you say, well, what's f of x? Well, it's this thing right here. F of x is going to be defined as a piecewise defined function. It's going to be defined as x plus 1 whenever x is less than 0. And it's going to be defined as the sine of x, and again, that's in radians, if x is greater than if x is greater than 0. Okay? So here it's undefined when x is equal to 0. Notice, we define it if x is less than 0. We define it if x is greater than 0. We didn't define it at all if x is equal to 0. But you know what? Even if it was defined for x equals to 0, that still wouldn't matter. Because when you're taking a limit, you don't care what happens at the point. Notice over here, we never actually cared about plugging in the number. If we did, we would never be able to get an answer. Plugging in the number doesn't actually happen. You worry about what happens when you plug in numbers close by. So even if I did have, I know exactly what happens when I plug in x is equal to 0, that still doesn't affect what's going to happen with the limit. The limit is found regardless of what happens at the point. All right, so here we go. Now, notice here, this is not a single function. It changes depending on what side of 0 you're on. So here, let's go ahead and find the limit as x approaches 0 from the right. Okay, well, if you're coming in from the right, that's this function. Because from the right, you need x to be greater than 0, which is this right here. So that's going to be of f of x. That's going to be the limit as x approaches 0 from the right of the sine of x. And we have to use that one because, again, we want to come in from the right. And if you're at the right of 0, this is the function you're using. If you were to the left of 0, this would be the function you're using. Okay, so let's go and do this one. Here, I can just do that by plugging in some numbers. Notice I only care about plugging in numbers that are greater than 0. Okay, so let's go and do that. That would be x, and here's f of x. And I only care about plugging in numbers that are greater than 0. So let me plug in 1, and 0.5, and 0.1, and 0.001. All right, so here we go. If I plug in 1, and again, I'm in radians, the sine of 1 is 0.8415. Okay, if I plug in 0.5, the sine of 0.5, that's going to be 0.479. If I plug in 0.1, the sine of 0.1 is 0.0998. If I plug in 0.001, take the sine of that, that's 0.0009. Okay, so here, do you plug in 0? Well, it turns out you can. You can take the sine of 0, but we don't. Because that's what a limit means. It means you never plugged in that number. It means you plugged in numbers that got close to that number. And as I plug in numbers that get closer and closer to 0, my y value is shrinking down and down to 0. So here the limit from the left as the limit from the right as x approaches 0 from the right of the sine of x is equal to 0. Because of this. But now let's see what happens from the left. If from the left you're also approaching 0, well then the two limits agree, in which case you have your answer. Your limit is 0. But if they disagree, that means your limit does not exist. So let's see which one it is. We're going to take the limit as x approaches 0 from the left of our function now. And that's the limit as x approaches 0 from the left. Well, if you're coming in from the left, you're using this one, this x plus 1. And let's see what that is. So we're going to plug in an x, and we're going to get an f of x. And now I want to get to 0 from the left side. Okay, so let me start with something like negative 1. Okay, let's see, negative 1 plus 1 is 0. Okay, well, let me get closer to 0. Let's say negative 0.5. Negative 0.5 plus 1 is 0.5. Let me get closer. Let's try negative 0.9. Oh, sorry, negative 0.1, not negative 0.9. Negative 0.1. If I take negative 0.1 plus 9, I get 0.9. And let's get really close to 0. Let's say negative 0.001. If I take negative 0.001 and I add 1, if I plug it in right here, that's going to give me 0.999. Okay, so what's happening here? Well, my numbers are getting bigger and bigger 0, 0.5, 0.9, 0.999. Oh, looks like I'm getting closer and closer to the number 1. So here, did I plug in the number 0? No, because the limit says you're not plugging in the number. You're plugging in numbers close to that 0. And in fact, here you're plugging in only from the left side. Okay, so we found our two-sided limits, and it turns out they're different from each other. Okay, so here, if they were the same, if they were both 0, then my answer would be 0. Or if they were both 1, then my answer would be 1. But since they're different, that means this limit is undefined. So the limit, let me just write it in notation. So the limit as x approaches 0 of f of x does not exist. And there's nothing you can do to fix that. It just does not exist. That's fine. Because these were different. Now, being able to evaluate a limit using these tables is one way to do it. Again, it's not a formal way to do it, but it does give you a good intuition. Another way to do it, however, is if you have access to the graph of that function. Let's consider a few graphs here. Here, I'm going to call these just graphs of f of x. I'm not going to worry about exactly what their equations are because it doesn't actually matter. Let's say I have, here's the graph of y equals f of x. Here's the graph of y equals g of x. Okay. Here's the graph of y equals h of x. And here's the graph of, let's say, y equals k of x. All right, so here are 4 different graphs. And exactly what are these functions doesn't really matter. So here I'm going to call this, on this graph, I'm going to call this number c, whatever it might be. Over here I'm going to call this one c. I'm going to call, over here I'm going to call this one c. And right here I'm going to call this one c. Okay? And then these are all just whole numbers, so that's 1, that's 2, that's 3. Here that's 1, that's 2, and that's 3. Here that's 1, 2, and 3. And over here that's 1, 2, and 3. All right, so without having these functions, we couldn't actually plug in any numbers. But so what? We can already read the ordered pairs here without any need to plug anything in. So first of all, in this case right here, what is f of c? Well, that's the number 3. Because look, if I plug in c into my function, I get 3. That had nothing to do with the limit. That's just what happens when you plug in a number into your graph. Right? That's something you could have done in algebra or even pre-algebra. Just read the graph. So f of c is equal to 3. Okay. What is the limit as x approaches c from the left? The way to think of that is, imagine you are standing right here on this curve, and you start walking to the right as you approach c. So as you start walking this way, what happens to your y value? Oh, well, your y value is getting closer and closer to being the number 3. I'm at 1, 1.5, 2, 2.5, 2.9, 2.99. Now remember, you're not allowed to actually reach c, but as you get closer and closer to c, that's going to get you closer and closer to the number 3. Now, what happens if I take the limit as x approaches c from the right? Well, the same thing. If I start right here, I'm at 3.2, and then 3.1, and then 3.01. And as I move closer and closer to my x value being c, remember I never actually get there, I only get close, it looks like my y value is getting closer and closer to the number 3. So in this case, plugging in the number, coming in from the left or coming in from the right, they're all the same. So that means that the limit as x approaches c, since the left and the right are equal to each other, that means overall the limit is 3. They're equal to those 3. Okay. Now let's consider this one right over here. Okay, right here, what is, this one's G. So what is G of C? That's undefined. Because notice, there's a hole in your graph. There's a discontinuity. So here, this is undefined. But I can still find the limits. Because what happens is I come in from the left. If I'm standing right here and I start walking to the right toward where my x is equal to c, what happens to my y value? Well, that's 1, 1.5, 2, 2.25. It looks like I'm getting closer and closer to 2.5. Okay, so if I take the limit as g approaches c from the left of my function, even though I can't plug in c, remember, when you take the limit, you don't actually try to plug in the number. You see what happens as you get closer to the number. And as you get closer to the number, the y value is going to 2.5. From the right, I would have the same thing. The limit as g approaches c from the right, well, again, my y value over here is 0.5, and then 1, 1.5, 2, 2.2, 2.4. As I'm getting closer and closer to x equals to c, my y value is coming up right here to 2.5. The way I've always thought of this is, if you cover that with your finger, what does it look like? If you follow the pattern, what does it look like the point should be? Oh, if I cover it with my finger, it looks like that value should be at 3. And over here, if I'm covering it with my finger, it looks like it should be at 2.5. Now, I uncover it and it is at 3. Awesome. Over here, I uncovered it and it's not at 2.5. But so what? It looked like it was at 3, and it looked like it was at 2.5. That's what we have always thought about the limit when it comes to a graph. It's not what's there, it's if I covered that point, what does it look like it does? Notice here the left and the right are both coming in to the same number, so that means that the limit as g approaches c, as x approaches c, I've been saying g, haven't I? The limit as x approaches c of g of x is equal to 2.5. Because the two sides are the same, that means that the limit overall is the same. All right, let's take a look at this one. What is that's h, right? So what is h of c? Well, that's equal to 3. Because if I plug in c, where's my y value? Oh, there's a hole right here. The point's actually up there. Okay, so when x is equal to c, y is equal to 3. Okay, so h of c is equal to 3. But now what about my limits? All right, if I take the limit as x approaches c from the right, again, that means I'm standing over here on the right, and I want to start walking toward the left, towards c. My y value is getting closer and closer to the number 2. Again, if I covered that up, where does it look like it's going? It looks like it'll end up right there at the number 2. The fact that it doesn't end up at 2 is irrelevant. Where did it look like it was going to go? Oh, the limit as x approaches c from the right of h of x, that's equal to 2. And from the left, you get the same thing. If you start from over here and move towards c from the left side, your y value is getting closer and closer to 2. So the limit as x approaches c from the left of h of x is equal to 2. But notice that these two are the same. And since they're the same, since they agree, that means that overall, the limit as x approaches c, not from the left or from the right, but overall, that's going to equal to 2 as well. Notice, sometimes these are the same. Sometimes they're different. And sometimes one's defined when one is not. And that's okay. Those are different from each other. Finally, for this one, if I take, what is this one, k? Let's take k of c. All right, if I plug in x is equal to c, looks like my y value is down here at 1. Here there's a hole. It's this one down here, the one that's filled in. So if I plug in x is equal to c, I get y is equal to 1. Okay, so k of c is equal to 1. Okay, now let's take the limit as x approaches c from the right. Well, if I'm starting from the right, that's this one on this side. If I stand right here and I start walking toward x is equal to c, my y value is going down. 2.5, 2.1, 1.8, 1.2. It's getting closer and closer to the number 1. So the limit as x approaches c from the right of k of x is equal to 1. What about from the left? The limit as x approaches c from the left of k of x, well, that's from this side. My y value is getting bigger. 1, 1.5, 2.1, 2.8, 2.99. It's getting bigger and bigger toward the number 3. Once again, if I were to cover those up, it doesn't matter what's there. It matters what looks like is there. If I come in from the right, it looks like my y value is going to come down here to 1. And if I come from the left, it looks like my y value is getting higher until it gets to 3. The fact that those points are or are not there is irrelevant. It's what does the path tell you? Where does it look like it's going? Notice here that the two-sided limits are different from each other. Right? From the right and from the left, I do not get the same value. They do not agree. So that means that overall, the limit as x approaches c, not from the left or from the right, but overall, does not exist. And there we go. Sometimes these are all exactly the same. Sometimes one is undefined and the other one is perfectly well defined. Or over here, the first one was defined and the last one was not. And sometimes they're all defined, but they happen to be different. All right, so let's go and give this one a try. Consider the following function. I'm just going to put it all as 1. Let's say you have the following graph. And again, this is 1, 2, 3, 4, and 5. All right, here we go. There's a hole right there. There's a point right there. There's a hole right there. This comes down to here. And there's the point up there. And then from here, that goes up and away. All right? So here is the point A, or rather the number A, the number B, and the number C. So go ahead and answer the following questions. Find the limit as x approaches A from the left. Oh, and here this whole thing is just y equals f of x. Find the limit as x approaches A from the left of f of x. Go ahead and find the limit as x approaches C from the right of f of x. Go ahead and find f of b. Go ahead and find the limit as x approaches b of f of x, not from the left or from the right, but just the limit. Find the limit as x approaches c of f of x, again, not from the left or right, just the limit. And then find f of c. Okay, go ahead and pause the video, give yourself the time that you need, and once you're done, go ahead and unpause and we'll go through that together. All right, so let's start with the nice ones. Here, these don't involve any limits. They are just plug in the numbers. So f of b, well, here's my b. All right, so what y value do I get when x is equal to b? Oh, right here, there's my point. It's 4. So f of b is 4. What about c? Well, here's my c, and my point is up there. Oh, that's at 3. Okay, so f of c is at 3. Notice that doesn't require any limits, doesn't require any sided anything. It's just, if here's my x, where's my y? Okay, but now these don't, it doesn't matter where your y is. It matters what happens as you approach that value. All right, so let's start with this one. Limit as x approaches a. Okay, well, here's my a. And I'm doing it from the left. Okay, so I'm starting from this side. As my x gets closer and closer to a, my y value keeps going up and up toward 2. So here this limit is equal to 2. Notice it's only the limit from the left. I didn't even worry about the right. Here, the limit is c approaches, the x approaches c from the right. Well, here's my c, and here's the right. I don't worry about that side. I don't care. Just this part. If I'm coming toward c from the right, it looks like my y value is going down and down and down toward the number 1. All right, 2.5, 2, 1.8, 1.6, 1.2. Looks like I'm getting closer and closer to the number 1. Okay. So it looks like my sided limit here, that's fine. That's equal to 1. And over here, that's equal to 2. But let's see our limits overall. The limit as x approaches b, not from the left or from the right, but overall. Okay, well, in order to determine whether the limit exists, you have to make sure that it's the same on both sides. Okay, so if I approach b from the left, I'm going up and up and up toward 4. As I approach from the right, I'm going up and up and up. Oh, but that's going toward 5. So here the limit from the left of b is 4, but the limit from the right of b is 5. Since those are not the same, that means this limit does not exist. Okay. Again, the idea is, if I were to cover that up, what looks like is happening? Well, I don't know. It doesn't. I mean, it kind of looks like it's going. It looks like there's a big jump. I'm not sure. It looks like it's going to 4, but it's also going to 5. I don't know. Oh, it does not exist because there's different things happening from either side. What about the limit as x approaches c? Okay, well, here's my c. As I'm approaching c from the left, well, that's shrinking down to 4, 3, 2. That's going down to 1. But from the right, well, we already knew that was going to 1. So from the left, it's going to 1. From the right, it's going to 1. So that means the two-sided limits agree, which means that overall, your limit is going to 1. And again, if you were to cover that, yeah, it's true. If you plug in the number c, you get 3. But that's not what we asked. We cared about what happens as you approach c, what happens along these paths. So if you cover that up, and you didn't know that was up there, and you were asked, okay, what happens as x gets closer to c? Well, it looks like you would meet up right about there at 1. So it is possible for you to take a limit and get one answer, and actually plug in the number and get a totally different answer. Because remember, here, you're not ever actually plugging in c. You're only plugging in numbers that are close to c. Here, you're never actually plugging in b. Notice, if you plug in b, you get 4, but you don't actually plug in b. You plug in numbers that get close to b, which is why these might be different. Yeah. So that brings us to the end of this topic, as well as the end of this section. If there are any questions, comments, or problems, please make a note of those and reach out. And I hope everyone has a nice day.